All right, so today we're going to be looking at implicit differentiation. So what this means is we're differentiating implicit functions. So first I want to quickly review what an implicit function is, and then we'll talk about how to differentiate them. This can throw a lot of students for a loop, but I think the way that I'm going to present it and suggest that you tackle these problems will help you greatly to not kind of get mixed up. So what are implicit functions, first of all? So implicit, from just common speak, means it's implied. It's an implied function. So y is an implied function of x, perhaps not meeting the definition of a function. So what does that mean to fulfill the definition of a function? It means that it has just one output for every one input, right? It passes the vertical line test as we reviewed at the start of the course. So we need y to be a single valued function for x. So one example of where that breaks down, where we say, well, this is definitely a function. It's represented out here in the 2 space, is x squared plus y squared equals 9. What does this look like? Well, this is really a circle of radius 3, right? If we remember from back in the day, so, something like this. It's got a radius of 3. And so here we have the problem where it breaks down that for a single input, let's call this, x naught. For a single input, I have 2 outputs, and that's a problem, right? Especially if we're talking about something like a paycheck function, right? You want the amount of time that you put in to be the same amount of pay either way. So you need one output per input. So geometrically, we see this issue arise here. And when we're talking about finding the instantaneous rate of change or the slope of the tangent line on a circle, it seems like that should be doable, right? This is a pretty simple curve. So how could I find the slope here? But really, the way we've defined it, I missed that one here. The way we've defined it is that the derivative function is a function of the input x. So here we would get 2 possible slopes, up here and down here, and obviously this works all the way across the circle. So to treat y as an implied function of x, and what we do is we use the chain rule is how we get around this problem. Okay, so and we just know that each point value around the curve for the output, it depends on both x and y. We can't just have y depending solely on x because we have this 2 output problem. Same down here with something like this curve, which when we graph it looks something like this. And then it has another piece coming down here like this. So again, same thing. If I wanted to find out what was happening here at x naught, I would actually have 3 possible outputs, which means I'd have 3 possible different slopes. This is just highlighting the issue that comes up a lot, especially in differential equations. There's a lot of implicit functions there. So that's further down the line. But we need to be able to differentiate these things because finding the slope at these points shouldn't be a problem. So what we do, again, like I said, is we use the chain rule. So these are the key points here. Assume y is a function of x. Differentiate the entire equation as if you were applying an operator, which you really are. Differentiate both sides of the equation and use the chain rule on y. Because y is some inner function of x that we don't quite know what it is, right? We don't have the formula for that f of x. Because if you tried to solve, all right, let's do a little brain bubble over here. If you tried to solve this for y, what you'd get is really plus and minus the square root of what, 9 minus x squared, which is really two functions. It's not one singular function. So I can't solve explicitly for y in terms of x, which is the issue. So we have to assume that y is some function of x. So let's cross this out. Assume that y is some function of x, differentiate both sides, and then use the chain rule whenever we differentiate y. So let's do that down below here. Okay, so let's say given x squared plus y squared equals 9, find dy dx. You might also be asked to find the slope of the tangent line at a certain point on the circle, which we would need dy dx for. There's a lot of types of problems that center on this. So finding dy dx, we'll do what we did before, which is assume y is a function of x, differentiate both sides with respect to x. So we'll take this x squared plus y squared equals 9. Give myself some space over here. And we'll differentiate both whole sides with respect to x. So what happens on the right is I'm left with 0. That's fine. On the left, remember that differentiation splits over addition. So we take the derivative of each of those two functions. So the derivative of x squared with respect to x is 2x, right, to the 2 minus 1, so that's just 2x, plus, and then derivative of y squared with respect to x. Well, again, you're assuming that y is some inner function of x, and so that's why I'm going to recommend you put brackets around y, because that will make you think of the chain rule, which is key to solving these problems. It's only using the chain rule that this actually works. So putting that around the y, because then we see, okay, this is really a function of x, and when I have that inner function of x, I apply the power rule on the outside, because it's raised to the power of 2, so this becomes 2 times that inner function y. Let me give myself some space over here. And then what's the second part of the chain rule? Derivative of the outer function times derivative of the inner function. Well, what's the derivative of the inner function? That's dy dx. The derivative of y with respect to x. We don't know what it is, but here we have access to it by using the chain rule, right? And so now we can solve for it, because this is now just a linear equation. So now you're solving for this guy. So we'll subtract 2x from both sides. So get 2y dy dx equals minus 2x, subtracting that from both sides. Divide both sides by 2y. And we'll get dy dx then must be negative x over y. So why does this make sense? Well, first of all, we can plug in a point, and I'll show you why it might make sense. But the other reason it makes sense is that it depends on both x and y. Right? That's important, because if this is the slope on the circle, it matters both coordinates where we're at. So up here, okay, a little interruption there, but where we're at, we were saying, why does this work geometrically, that the derivative would be negative x over y? So up at the top, we see that the slope of the tangent line would be at 0, and we know that since the x-coordinate is 0, negative 0 over y, that works, right? But for one that's a little bit more interesting, let's say like this red one, here this would be at, about 45 degrees of angular rotation. So this would be sitting right at that kind of corner of the circle where the x and y coordinates would be equal, and that would be at 3 radical 2, 3 radical 2. And so we could compute the slope there, the slope of the tangent line, at 3 over radical 2, 3 over radical 2. And that's what, negative 3 over radical 2 over 3 over radical 2, which is negative 1, which makes sense with what we'd expect over here, that this seems to be going down 1 over 1, down 1 over 1. Right? And so for any point along the circle, you can compute this, but it requires both x and y because it's an implied function of x, right? You need both of those. So through the chain rule, this is how you get access to dy dx. So let's do one more here to highlight this process. So differentiate to find dy dx for, let's do that curve we had before, y cubed minus xy equals -6. So again, assume y is some inner function of x. So what you can do is even put in some brackets here to remind yourself, because this is a place where students make the most mistakes typically, forgetting to apply the chain rule in multiple spots. So here, differentiating everything with respect to x. The right-hand side nicely is just 0. On the left-hand side, again, we've got the power rule times the chain rule for that inner derivative there. And then for this piece, this minus xy, this is x times y. I've got a product of two functions, so I actually need to use the product rule here. So minus the derivative of x is just 1. I'll put everything in brackets here. So minus 1 times y plus x times the derivative of y we know is dy dx. You'll notice I'm putting that whole thing in brackets because I'm subtracting the derivative of xy. So that's that whole thing in brackets. And then over here, plopping in back that y. So this came from here. Chain rule here and chain rule here. Because I had two kind of instances of y, so I needed to use the chain rule twice there. So I hope that makes sense. So from here, now isolating again, we want to solve for dy dx. So I'm going to start to isolate dy dx as my variable and that I'm solving for, and move everything else to the other side of the equation. So I'm going to go ahead and carry out this subtraction. So this becomes 3y squared dy dx. You might want to keep brackets around the dy dx so you kind of know what you're hunting for. And then it says minus x dy dx. So from here, another skill that's kind of rusty is using factoring. So maybe we'll add this y to both sides first before we take care of that. 3y squared times dy dx minus x times dy dx equals y. Remember, we're solving for this. So what we'd like to do is actually factor this to the outside of this expression. We'll get dy dx times what's left, which is 3y squared minus x. Right? And then divide both sides by this 3y squared minus x to solve for dy dx. This must be equal to y over 3y squared minus x, and that's a y. Again, your answer is most likely going to depend on x and y for the coordinates on that curve, because as we saw before here, this function has many outputs for certain inputs of x. So I hope that makes sense and that we get some good questions going in the class discussion. Enjoy the practice problems. We'll see you out there.